So you got a simple scheme here for how to solve this thing. The future given the present. Okay, simple formula. Now, there's a problem with this formula. Because every time you set up an iteration, it is not guaranteed that this iteration is actually going to follow the solution correctly. Like, we haven't talked about that yet. There's this idea of what's called stability of a scheme. We're going to talk about that in the next lectures. But the idea is if I start iterating along, there are iteration schemes that blow up. You start iterating, and things go to infinity. So that's not cool. First of all, it's wrong. Second of all, you better know what schemes do this, because you don't want to start implementing, like, check this out. I solve this equation. Things are going to blow up. It could be just because your iteration scheme blows up. Okay? So we have to address that issue. So it's not just about I have a scheme to get forward in the future. I have to know something about its accuracy and its stability. So these are two things we still need to address with this. Okay. Now, more generally, you can think about taking this scheme idea and say, well, actually, I can sort of generalize this concept here to think about the following, which is it gives me a way to think about solving a differential equation by something like this, okay? Which is, I can set up an iteration scheme where my future is what it is now plus a little bit of something. And Euler is just one way to do this, right? Euler is like the most simple-minded way to do a stepping forward scheme. But we can think about, well, maybe I can pick fancier things here and do the same thing. Okay, and maybe even get something more accurate and stable. All right, so how would we motivate something like this? Well, let me tell you first of all about what this scheme actually does graphically. Okay, so what we're going to do here is, suppose we're going to step forward into the future, t0, t1, t2, t3. So we have a delta t between them. And we start off with some y0 value. Okay, so up here somewhere, we start here. Now, let's suppose I actually can solve this thing exactly for a moment. So here's my exact solution. So presumably what I'm trying to do with this scheme is trying to say, really what I want to do is calculate that exact solution very accurately. Okay? All right. So what does this Euler scheme do? How does it predict where T1 sits? So let's go back here and ask a question real quick about this scheme. It says, my solution in the future is what it is now plus a little bit of something. What is this little bit of something all about? F. What's F? F. Well, it's the right-hand side. It's the derivative. Well, derivative is a what? Slope. So I am basically using the slope, which is F, to predict my next point. So graphically, what this looks like is basically what you're saying in that Euler scheme is say, here I am. To get into the future, I think about taking off on the slope line to that. There's my slope. It's F. And here's where I am at time t1. This is the actual solution. There's my prediction. You can see I made an error. So it's going to be important for us to quantify that error. Okay, if I were to do it again, what I do is actually take this value, plug it into that F to try to get this slope here, and take off on that slope to get to here. Then take off on this slope to get to here, so forth. So here are my numerical solutions. Here's the exact. And you can see I'm falling off this thing. But you can also see that if I take my delta t to be smaller and smaller and smaller, right, then I can get closer and closer to this curve. Notice there's something very intuitive that happens here, which is it's taking off sort of in a slope in the right direction. Now, how would you maybe think about coming up with a better scheme? Euler just says take off on the slope from there. But notice, well, maybe I could if you knew, for instance, what was gone over here, maybe you could use the fact that I know that the slope is changing over here somehow, so I could maybe use slope information here. Maybe I could use slope information midway through. In other words, why do I just use the slope on the left? Maybe I could calculate some kind of, roughly some slope over here and sort of average them so that if I took this slope and somehow half of it's this slope, half of this slope, maybe I could use those two together. So instead of coming off down here, since I know the slope's going to be a little bit flatter here, I could use this plus this and maybe make a prediction that would come down to here. Maybe be a little more accurate. Okay? This is the whole idea behind what are called higher order schemes. So let me give you the concept. The concept is the following. What I want to do now then is say, I want to predict my future point, the current point, plus delta t times, here's a general way to think about framing this in one way, or one specific way. Let me write this down, and I'll explain the terms. Okay, there's a bunch of terms here. Notice what I'm going to do is the following. Let me explain what happens. My solution in the future is what it is now plus something. And what I've done here is said, I'm going to do the following. What is my little bit of something? A times f of ty. This is the slope on the left. Okay? So this is my slope where I'm starting from. What about this over here? Plus b amount of this. So there's a of this, there's b of this, and there's b amount of this, and what do I have of this? T plus p delta t. I'm evaluating it not at some p delta t. In other words, if I pick p to be 0, it'd be evaluated on the left. If p is 1, it's evaluated at delta t, so all the way on the right. If p is a half, it's evaluated halfway between. And then I can also pick q here. So I have 4 constants that I can pick, all with the express intent of making for a higher order scheme for accuracy. Okay? So if you do a Taylor expansion of this and of this, turns out you get the following. You find the following relationships have to hold. A plus b is 1, p times b is a half, and b times q is a half. I have 3 equations, 4 unknowns. Okay, so I have 1 degree of freedom here. I can pick one parameter to be anything I want it to be, and then the others are constrained. So I have an infinite number of choices. So if you're into numerical analysis, you are like, yes, there's a PhD thesis right there. By the way, it's already been done, so don't get any ideas. Right? So, but that's what people did in the early days. Hey, what can I do with this? I have a lot of freedom. Can I come up with better and better schemes by just simply playing around with these constants?